Hey, so I went to a few physics lectures this semester at school, and I'm here to talk about one that I found particularly interesting. It was the last one, Cosmic Rays, Alien Invaders from Outer Space. The speaker was Namak Ot. Uh, I don't know if I said that right, not sure. But yeah, I just want to talk to you guys a little bit about that. What are some of the things that I think were more important that you didn't really talk about, but pretty critical to the lecture. And this is about muons. He talks about a lot about muons and nuons and pions in the lecture, and he doesn't really talk about what they are. So I just want to open that up for you guys. So what is a muon? A muon, it comes from the Standard Model, and it's basically a theory for subatomic particles. And these are things that are smaller than electrons, protons, and neutrons. There's four categories: uh, quarks, leptons, Gauss bosons, and Higgs bosons. Muons, pions, and neutrinos. These are things he talks about the most. They're actually found in the leptons. It's kind of like a subcategory of electrons, so the subatomic particles that make up more or less electrons. Um, Now, where do muons come from? This is where it ties into lecture a whole lot. What he was talking about is that they actually come from upper atmosphere. So cosmic rays come in and they into the upper atmosphere, and they basically collide and then decay. And during that collision decaying process, muons are created. So going into this, I knew a little bit about the Standard Model and how these subatomic particles. Kind of knew a little bit about them. Uh, this lecture, him talking, really expanded my interest level in that. Also, so let's talk about some of the physics behind the lecture. So you talk about the origins of the cosmic rays. So they come from space. I'll talk more about it later, but they come from neutron stars decaying, more or less, pulsars, supermassive black holes, supernovas, like the stuff like that. These are stronger up in the higher atmosphere than lower. That kind of comes from how they just decay, and they decay very quickly on the order of nanoseconds. So of course higher up you see them more often. Uh, Now why are muons, neutrons, and that kind of neutrinos, that kind of stuff, and cosmic rays, why is that important? Well, it's important because one, it affects our everyday life, and it affects like electronics and stuff like that. Um, Also, because it's kind of cool to know about neutron stars and that sort of stuff, helps us detect them and figure out where it is. So some of the methods used to detect these is for muons especially is the Peri Argur Observatory in Argentina. It's 3,000 kilometers square, like square kilometers. So it's pretty massive, and it's pretty massive because even though these are hitting the atmosphere all the time and kind of hitting all around us all the time, they're so faint when they hit the atmosphere, when they finally make it down to the ground, that you need these large like detectors to detect this faintness. Uh, most likely, most of the things we don't really like the muons because they are actually really massive, about 150 times the massive electron. So the electromagnetic field affects this greatly. Neutrinos, these are a little bit more accurate of figuring out the cosmic rays. Uh, so because they're massless, and because they're massless, electromagnetic forces are not going to affect it as much. So these go in a straight line. One of the neutrino detectors is the ice cube in South Pole. It's 400 feet deep. So basically, they just drill these deep holes, 400 feet deep, to detect neutrinos. And this is because when they interact with matter, uh, molecules and whatnot, they actually emit light. And that's really cool. But to detect this light, you need something that's massive because there's not that many hitting it. They're in their orders, magnitudes of 1 or 2 per square meter per century, something very, very faint like that. So you have to have these massive, massive detectors to detect these faint, faint neutrinos. Now this is the one that the professor talking used the most, and this is actually what his interest is gamma rays. Gamma rays. So gamma rays, if you know the electromagnetic spectrum, with the visible light and all that, radio waves are on the very, very far left lane side. Gamma rays on the very, very far right side, because it's a very, very high frequency, incredibly high energetic wave. This is a result of a few decaying matters. It's either decay of a pion, not. Also, there's some other methods, like inverse Capone, a scattering, kind of two electrons kind of hit. Some other methods, but basically, gamma rays they come from just sources in outer space, and just general from gamma ray bursts, and so on and so forth. These, because they are massless, because it is a rave. I mean, it's electromagnetic wave, but more or less, it is a rave, travels the speed of light. So these will more or less go in a straight line. They're fairly easy to detect, especially on the gamma ray energies that we can detect from outer space, and it's a 1 giga electron volt to 1 to 10 tera electron volts. So they're massively, massively energetic. So that's kind of cool. So again, so where do these come from? They come from neutron stars. Some of it comes from neutron stars being sucked into a black hole, and because of that, it's spitting out a ton of energy as this neutron star, which is basically the core of a dead star. Super, super, super massive. It is on the orders of neutron stars, usually 100 kilometers, 1,000 kilometers in diameter, and it's on the order of 10 or 20 of our sun masses in that. So just picture that. It's incredibly, incredibly massive. Another one is a pulsar. That's basically a neutron star that gets spinning really incredibly fast. Like 1,000 revolutions per second, faster than that. It is incredibly spinning fast. And by that, it kind of pulses. And those pulses, that pulse that gives it the pulsar is actually an energy burst. We can detect in cosmic rays and so on and so forth. Then you have supernovas. We all know what supernovas are. That's when a star just explodes. And by that exploding, it releases energy, which in turn causes cosmic rays. Another is a starburst. And that's basically when a star gets too energetic and needs to release some energy, and it just bursts. A ton of energy that causes cosmic rays again. These cosmic rays coming at us from all over the universe is hitting our Earth all the time, and that's causing all these muons and neutrinos and all these subatomic particles just to be created when they hit us. So what I learned from this was that these particles are everywhere. They're always hitting us. He brought out a detector there, and it made a sound whenever a particle hit it. It was beeping all the time, which is just mind-blowing. That a subatomic particle caused by energy from a neutron star or other source, many, many, many thousands, hundreds of light years away. And a light year, that's how fast light goes in a year. And light's the fastest thing there is. So just imagine, it's ridiculously far away, and it's affecting my life indirectly, directly. It doesn't really matter, but it's affecting it in anyways, and that's just mind blowing. Some other cool things about just this that really sparked my curiosity and really just intrigued me a whole lot. Other than just the fact that I love this kind of stuff, this is my passion. Is this astronomy and stuff like this? Is that carbon radiocarbon dating? The things that everyone uses to basically date really old stuff. It actually uses carbon-14. You might not know, but carbon-14 actually comes from cosmic rays, which is just mind-blowing. So something that we actually use all the time to date stuff comes from the cosmos. Another thing is FX electronics, and this is really kind of cool. My professor at school kind of talked through us this, but air, so sparks, electricity, so sparks in the air. Air is a really good insulator, and it should actually not spark at the experimented and tested uh, electrical fields that it does. And it actually sparks this because neurons actually hit nitrogen and oxygens, knocking off free electrons. And those free electrons actually add up and cause sparks. And if they add up a whole lot, they actually cause lightning. And that's just ridiculous. So all these free electrons, these muons from outer space, is causing like little free electrons, and that can actually mess up electronics, and that's kind of really cool. So, in all, it was a really fun lecture. I just found it really exciting. So, just thank you for watching this video, and I hope you enjoyed it.